So in hexagonal close packed crystals, we have simple hexagonal unit cell. This is the simple arrangement of the unit cell. Now, how to calculate rank of the simple hexagonal unit cell? Rank is nothing but number of atoms per unit cell. You can calculate rank by using this formula, number of corner atoms into 1 by 6, because each corner atom is shared by 6 unit cell in hexagonal close packed crystal. Okay, plus number of body center atoms. I have told you, if the atom is present inside the unit cell, it is not shared by other unit cell. So whatever atoms present at the center, okay, you should take all the atoms, okay, just for counting. Then we have two face center atoms, one at the top, the other one at the bottom. Face center atoms are shared by 2 unit cell. So number of face center atoms, and each face center atom is shared by 2 unit cells. So the contribution to 1 unit cell is 1 by 2. Okay. Now what I'm going to do, I'll substitute the atoms. So we have total 12 corner atoms. So 12 into 1 by 6 plus, and we have 3 body center atoms, 3 plus we have 2 face center atoms, 2 into 1 by 2. Okay, so we'll get 2 plus 3 plus 1, we'll get 6. So rank of simple hexagonal unit cell is 6, which we discussed already. Okay, now I'm going to calculate the packing fraction of hexagonal close packed crystal, right? How to calculate packing fraction. Yeah. Okay, now how to calculate packing fraction. You know very well packing fraction. Let me write packing fraction simply as PF. Packing fraction is nothing but rank of the unit cell, which gives you number of atoms present per unit cell into volume of each atom. Each atom, we assume atoms as spherical in shape, therefore each atom has volume 4 by 3 pi r cube, where r is the radius of the atom, divided by volume of the unit cell. Volume of the unit cell, this is the formula. Okay, now volume of the unit cell, observe this carefully. Now we have a structure which is hexagonal, right? Therefore, what's the volume of the unit cell? How to calculate, right? So for a simple hexagonal unit cell, volume of the unit cell is nothing but base area of the unit cell into height. Okay, base area into height. If you observe the base, this is the unit cell, the base appears like an hexagon. Okay, it's a perfect hexagon. So let me draw like this. So the base appears like a perfect hexagon. A perfect hexagon. You can divide this hexagon into 6 equilateral triangles. Okay, you can divide this into 6 equilateral triangles. Now, what is the area of an equilateral triangle? Students, anyone? Anyone can answer this? What is the area of an equilateral triangle? Equilateral triangle. Any idea?
Root 3 by 4 a square.
Very good. Root 3 by 4 a square. Okay. Therefore, area of this hexagon, okay, base area, also called base area. Base area is nothing but we have 6 equilateral triangles. So 6 into root 3 by 4 a square, where a is the edge length. Where a is the edge length. And remember, here we have an atom, here we have an atom, here we have an atom. So all the corners are occupied by atoms, and we have an atom at the center. Right? Actually speaking, these corner atoms, right, they are actually touching each other. Right? They are touching each other. Therefore, the centers of the two corner atoms, right, the adjacent corner atoms, right, will give you the edge length. So this is the edge length of the unit cell. And here, since the atoms are similar atoms, identical atoms, so radius of this atom and radius of this atoms are same. Therefore, A should be equal to 2R. A should be equal to 2R. Okay, keep this in mind, very, very important. Right? So if I introduce this A value here, I'll get 6 into root 3 by 4 into, since A is 2R, AR square, A square is 4R square. Okay, this 4 and this 4 cancels, so you'll get 6 into root 3 into R square. This is the base area of this hexagonal face. Okay, base area of the hexagonal face. Now we need to calculate the height of the unit cell. Okay, how to calculate the height of the unit cell? See what is meant by height here. See, this is the height. This is the height of the unit cell. Right? You take this layer and this layer. Okay, and this length is what we call as height. Right? Listen, suppose, see, I have 3 layers here. Suppose if the atoms are present, students, if the atoms are present one over another like this, okay, this is first layer atom, second layer atom, third layer atom. If suppose if we place the atoms like this, then the height supposed to be equal to 4R. Okay, am I right, students? If the first layer, second layer, and third layer atoms are present one over another like this, then height should be equal to 4R. Am I right? Student, is it correct?
Yes. Yes, sir.
Okay, but actually what actually here present here is, listen, these atoms are not placed one over another. Actually, the second layer atom is present in the depressions of the first layer. I told you, right? It is present in the depressions of the layer, in the first layer. Therefore, H is not equal to 4R. Right? But we can derive mathematically by using the geometry idea. Okay, I'm not going to do that, but you can do. Right? It's very simple only. H is equal to, H is supposed to be 4R if the atoms are placed one over another like that. But I have told you the atoms are placed in the depressions. Therefore, H is not equal to 4R, but H is equal to 4R times square root of 2 by 3. This you can show by using geometry methods. Okay, you can take right angle, triangle, and you can find this very simple one you can do. But what I am going to do, I'll take this value as such and I'll calculate the packing fraction. Okay, students, why I am multiplying by this square root of 2 by 3? Because it is, if H is equal to 4R, it means the atoms are placed exactly one over another. But in hexagonal closed packed crystal, you know very well, atoms are placed in the depressions. Therefore, H is not equal to 4R. Okay, actually H is equal to 4R times square root of 2 by 3. Square root of 2 by 3. Okay, so this is the value of the height of the unit cell. Now, what is the packing fraction? How to calculate? It says, now we got the height and we have the base area. Therefore, first let me calculate volume. Volume of the unit cell. Volume of the unit cell. You know very well, volume of the unit cell is nothing but base area into height. What's the base area? We have calculated base area 6 into root 3 into R square. This is the base area. And height of the unit cell is 4R into square root of 2 by 3. This is the height of the unit cell. So this root 3 and this root 3 cancels. Okay. So if you multiply, you'll get 6 into 4, 24. R square into R is R cube. And here we have square root of 2. This is the volume of the unit cell. Students, turn on your camera. Everyone. Yeah. Is this correct? Any doubt up to this?
No.
Yeah, so this is the volume of the unit cell. Okay, now let me go back to the packing fraction for formula. Packing fraction equal to, you know very well, rank of the unit cell. For simple hexagonal unit cell, rank is 6. Okay, just now we calculated 6 into volume of each atom is 4 by 3 pi r cube over volume of the unit cell, which is 24 into r cube into square root of 2. Right? This r cube and this r cube cancel. Right? Here we have 24, this 24, this 24 cancel. So you'll get 1 by 3 into pi value is 22 by 7. Okay? Into 1 by square root of 2. 1 by square root of 2. If you simplify this, okay, you will get exactly 0.74. So packing fraction for simple hexagonal unit cell is 0.74, which is same as the packing fraction for FCC unit cell. Correct? We discussed face-centered cubic unit cell where we got the same packing fraction. Hexagonal unit cell also has the same packing fraction 0.74. So percentage packing fraction is equal to 74%. 74% of the unit cell is occupied by atoms. The remaining 26% okay, exists as a empty space. Right? So this is regarding the hexagonal close packed crystal. So in hexagonal close packed crystal, packing fraction is 0.74. Okay, so keep this in mind and remember the height formula and the base area formula, right? Based on this, several questions may appear in the entrance examinations. Okay, yeah. Is there any doubt in this, students? Do you have any doubt?
No doubts, sir.
Students, if you have any doubt, you can ask me. Is it clear?
No, sir.
Yeah. Yes, so this is the method of finding.
Yes.
Okay, yeah. This is the method of finding packing fraction for hexagonal close packed crystal. Okay, now we'll discuss another important information called diamond cubic crystal. Diamond cubic crystal. This is very, very important for entrance examinations. Diamond cubic crystal. Okay. Yeah, what is meant by diamond cubic crystal? You know very well, diamond forms crystal. Okay, very specifically covalent crystal, right? And I have also told you in diamond we have many number of adamantine units. Okay, so let me just draw that just to make you remember. We have already discussed this, right? This is called adamantine unit, right? If you extend the adamantine unit like this, right? So many adamantines, you can make many adamantines together like this, right? If many adamantine units, right, combine together, right, you will get what is called diamond. Adamantines are very rigid molecules. Okay, that's why diamond is very hard. I told you already. Okay, but how this diamond, right, exists in the crystal lattice? Okay, in crystal lattice, how this diamond exists, right? Diamond actually forms FCC unit cell. Diamond, okay, diamond crystal or diamond cubic crystal. It's a cubic crystal basically. Diamond is a cubic crystal which consists of FCC unit cell, plus 4 additional atoms. 4 additional atoms present at the body diagonal. 4 additional atoms present at the body diagonal. Body diagonals. Okay, diamond cubic crystal has FCC unit cell. Okay, the unit cell is FCC. In this unit cell, okay, 4 additional atoms present at the body diagonals. Okay, what is meant by that? Okay, first let me draw the FCC unit cell. You know very well an FCC unit cell looks like this. FCC unit cell has 8, all the corners are occupied by atoms. Okay, in FCC unit cell, all corners are occupied by atoms, all corners, right? And these atoms are carbon atoms here because we are talking about diamond. You know very well diamond consists of only carbon atom, right? So all the corners are carbon atoms. Then we have carbon atom at the face centers, top face center, this side and this side, bottom face center, front and back face centers. Atoms present at the corners as well as face centers. This is FCC. Additionally, okay, I am going to place 4 more atoms in this unit cell. Okay, let me separately show you how I am going to place the 4 atoms. Then I'll include those 4 atoms in this unit cell. Okay, let me show you that separately first. See what I'm going to do. In the diamond cubic unit cell, right? Now I'm going to draw body diagonal. Students, listen. I'll take this corner and I'm going to join in this with this corner. This is one body diagonal. You have to connect opposite corners. Opposite corners. Okay. Then, and in this body diagonal, I'm going to place an atom. Okay, at this position. I'll place one atom at this position. Okay. Suppose if this corner is origin. If you take this corner as origin, what is origin? X value is 0, Y value is 0, Z value is 0. Okay. Suppose if you take this corner as origin, then this atom supposed to present at X value of 1 by 4, Y value of 1 by 4, Z value of 1 by 4. So this atom has the coordinates, let me write here, X value 1 by 4, Y value 1 by 4, Z value also 1 by 4. That is the position of one carbon atom in the unit cell. Okay. I am just showing the additional 4 carbon atoms, right? Additional 4 carbon atoms. One carbon atom present in this body diagonal. Then another carbon atom, I'll take another body diagonal and show you. Now, let me connect this corner with this corner. Okay. If you follow this diagram carefully, then only you can easily understand. Otherwise, it's difficult. Yeah. Now, in the second body diagonal, I'll place the atom, okay, close to this corner. Okay, close to this corner. I'll place here. I'll place it here. Okay. So this atom, right? This atom has an X value of 3 by 4. Okay. This atom has it has an X value of 1 by 4. And right here. See, this is X axis, so that you can easily understand. Okay, this is Y axis, this is Z axis. Okay, suppose if I fix like that, then this atom, right, is present, and it has an X value of 1 by 4, Y value 3 by 4, and Z value also 3 by 4. So that is the position of the second carbon atom. Students, observe this carefully. I will discuss about this about these coordinates, okay, a little later. Right? Then third body diagonal, let me draw here from this corner to this corner, third body diagonal. Okay, in this body diagonal, I'll keep the atom at this position, near to this corner, near to this corner. Okay, and the position of this atom, the position of this atom is X value 3 by 4, Y value 3 by 4, X 3 by 4, Y 3 by 4, Z value is 1 by because it is close to this corner, therefore Z value should be low, so 1 by 4. Then I'll take the next body diagonal, that is this diagonal. This body diagonal. You know very well a cube has 8 body, a cube has 4 body diagonals. Okay, so these are the 4, and in the last one I'll place the carbon atom, okay, near to this corner, okay. This is the 4th atom. Okay, and what is the position of that atom in the unit cell? The position of this atom, right, in the unit cell is X value 3 by 4. Okay, Y value is 1 by 4 and Z value 3 by 4. That is the position of the 4th atom. Students, it's very simple. You place 2 atoms at the bottom of the diagonals and 2 atoms at the top of the diagonal. Okay, alternatively you have to place. See here, bottom. Okay, here I put it in the top. Similarly, here I put it in the bottom. For this diagonal, I put it in the top. Alternatively, you have to do. Okay, now listen. I am going to place these 4 atoms in this unit cell. Actually, it is present in the unit cell, right? Okay, you first take an FCC unit cell, right? I am going to place these 4 atoms in this FCC unit cell. Okay, so let me draw this in this diagram so that it makes it appears somewhat difficult to follow. That's why I've drawn this separately. Okay. Yeah. So we have 4 body diagonals. 4 body diagonals. Okay. And these are the atoms. So here I place 1 carbon atom, right? And here I'll place 1 carbon atom. Here I'll place 1 carbon atom, and here I'll place 1 carbon atom. Is this clear? Students, the idea is very simple. You take an FCC unit cell, place 4 atoms in the body diagonals. Okay, and the 4 atoms supposed to be placed like this, right? If you place it, you will get what is called diamond cubic crystal. Any doubt, students? Any doubt in this?
No doubt.
Is it clear?
Yes, sir.
Hello, students?
Yes, sir.
Okay, so this is diamond cubic structure. Now, in diamond cubic lattice, in diamond cubic crystal, one unit cell consists of, okay, how many atoms? That is rank. What is the rank of diamond, the unit cell present in diamond cubic crystal? Okay, let me write in the next page. Rank of the unit cell. Rank of the right here. What is the rank of the unit cell? Rank of the unit cell present in diamond cubic crystal. I wrote simply DC. DC means diamond cubic crystal. Okay. How to calculate the rank? Very simple. We have corner atoms. You know very well, in cube, corner atoms are shared by 8 unit cells. We have face center atoms. Face center atoms are shared by 2 unit cells, so you have to multiply 1 by 2. Then take the body centers, add them as such. Okay, this is the formula for rank. Okay. Now, how many corner atoms are there? Okay, since it is an FCC unit cell, we have 8 corner atoms. So 8 into 1 by 8 plus we have 6 faces. So 6 face center atoms into 1 by 2 plus we have 4 atoms inside the unit cell. Okay, inside the unit cell, you take those atoms as body center atoms. They are not exactly at the body center, but you can assume that these 4 atoms are not shared by other unit cells. Okay, so I am considering these 4 atoms as body center atoms. So we have 4 additional body center atoms. Okay, so what's the value? 1 plus 3 plus 4. I'll get 8. So rank of the unit cell in diamond cubic crystal is 8. Students, this is very important for your entrance examinations. Okay, if you write any entrance examinations, okay, this data is very useful. Keep this in mind. Right? Any doubt, students? Any doubt in this?
No doubt, sir.
Okay, yeah. So now you know what is the rank of simple cubic unit cell. Let me just summarize that. Listen, you know very well rank for different unit cells. Okay, so rank and unit cells. Unit cell. Okay, for simple cubic unit cell, rank is 1. For body centered cubic unit cell, rank is 2. For face centered cubic unit cell, rank is 4. For hexagonal, simple hexagonal unit cell, let me write like this: simple hexagonal unit cell. For simple hexagonal unit cell, rank is 6. For diamond cubic unit cell, rank is 8. Okay? Remember this. This is very, very important data. You can also calculate packing fraction. Naturally, packing fraction for diamond cubic will be very, very high because the rank is so high. So the packing fraction will also be high. Okay? It's the hardest material, right? Right. So these two informations are very important. Keep it in mind. Now, what I'm going to do, voids in crystals. Okay. The next one I'm going to discuss is voids in crystals. Voids in crystals. Voids in crystals. Actually, voids means the empty spaces. Actually, right? The empty spaces in crystal. Right. See, there are two types of voids in crystals. Okay. In voids, there are two types of voids in crystal. Number one, tetrahedral void. And number two, octahedral void. When a crystal is formed, right, whether it forms simple cubic, BCC, FCC, hexagonal, whatever it is, in all crystals, voids exist. Okay, we have two types of voids, tetrahedral void and octahedral void. What is meant by tetrahedral void? Okay, what is meant by tetrahedral void? Listen, suppose I'll take three atoms, or just imagine atoms as a ball. Imagine, okay, atoms as ball. You place three balls like this close to each other, and there is a depression in the middle, and you place one ball over the top. Students, listen carefully. You take three balls, okay, keep them together. You will get a depression at the middle. Place another ball in the depression. Okay. Now, listen. If you connect the centers of the four balls, okay, below we have a triangle. Right, we have three atoms. So if you join the centers of the three atoms, right, you will get a triangle. And if you join with the center of the top atom, okay, you will get a structure, something look like this. What is the structure called, students? Actually, we have an atom here, 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 and here. Yes. What is the structure called, students?
Filament.
It's a tetrahedron, right? We have three balls below, one ball above. Correct? The structure looks like a tetrahedron, right? Tetrahedron. Right? Listen, the middle of this tetrahedron, that is the middle of these four balls, okay, has some gap. Okay, that gap, that empty space is what we call as tetrahedral void. Right? The middle of these four balls. Okay, the middle place of these balls, right, has some gap or the empty space. That empty space is called tetrahedral void. Why it is tetrahedral? Because if we join the centers of these four balls, you'll get a tetrahedron. And the mid space or the space inside this tetrahedron, which is empty space, and that space is called tetrahedral void actually. Is it clear, student? Any doubt in this? Students, any doubt in this?
No doubt, sir.
Yeah, this is called tetrahedral void. What about octahedral void? What about octahedral void? What is meant by that? In octahedral void, listen, I'll place three atoms like this. I'll take three atoms. I'll place it like this, three atoms. Okay, and I'll place three more atoms above these. Assume that this is the bottom layer. I'm going to place one more layer over this in such a manner that I'll place one atom here and two atoms like this. Students, are you able to understand this? We have three atoms below and three atoms above. I have placed the three atoms like this. Okay? Students, are you able to follow this? Now, the center of this space, the center of this space is what we call as octahedral void. Octahedral void. Give me some time. I'll bring balls so that you can easily understand that. Give me a few minutes. Students, hello? Students, listen. And let me place balls like this. Listen. If I place three balls like this, see, I'm placing three balls like this. You will get a depression at the middle, right? Now I'm placing the fourth ball in the depression, right? I'm placing the fourth ball in the depression. Okay. Now look, this structure appears like this, right? We have three balls below and one ball at the top. If we join the centers of the four balls, you will get a tetrahedron. You will get a tetrahedron, and the middle space. Okay, there is an empty space at the center of all these four balls. That empty space is what we call as tetrahedral void. Students, is it clear? Any doubt? Okay, this is tetrahedral void. Now let me show you octahedral void. I'll take we require two more balls. Let me take that. See, I'll place like this. See, I took three balls like this, and I took three balls like this. Now I'm placing the balls in this manner. See, it forms a triangle. Now I'm placing the three balls above like this. Okay, by appearance, see what I'm just showing this one. Okay, we have three balls below and three balls above. right? Listen, if I just turn this structure, students, see this, how this structure look like? How this structure look like? We have 4 atoms at the middle and 1 atom at the top and 1 atom at the bottom. Is it correct? Students, are you able to see this? Right? See? If right, in this, what I'm showing to,
Yes, sir.
right, this structure consists of, see, 4 atoms, right, present at the, are forms one layer, and we have 1 atom at the top and 1 atom is present below. Now if you join all the 6 atoms, or the 6 centers of the atoms, students, if we join the centers of all the 6 atoms, you will get a structure called octahedron. Okay, let me show you again. See, I took 3 atoms and I'm placing 3 atoms above like this. Okay, I'm placing 3 atoms above like this. Now, right, this structure is octahedron. How to understand whether it is octahedron or not? For this, I'll just turn this like this. Now, if you see, we have 4 atoms which form a regular square, and above this we have 1 atom, and below this we have one more atom below. Therefore, if you join the centers of all the 6 atoms, okay, you will get a structure, something looks like this. If you join the centers, so I have an atom here, 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 and here, then we have an atom below. If you join the centers of all the 6 atoms, you will get a shape. That shape is look like an octahedron. Am I right, students? Is it clear? Any doubt? If you see this structure, it doesn't show you, or it doesn't convey that the structure has octahedron. You cannot understand that. So what, for that purpose, see what I did? I took 3 balls and I took another 3 balls like this. Okay, if I place the balls in such a manner that, okay, if I place the balls like this, right, you can see this structure. This structure is, you can see, but you cannot get the idea of octahedron. For this, what you have to do, you have to just tilt the structure. Just tilt the structure. If you see like this, then we have 4 atoms forms a square. We have 1 atom at the top and we have 1 atom at the bottom. We have 1 atom at the bottom. Right? If you join the centers of all the 6 atoms, you will get an octahedron, a perfect octahedron. Right? The center, the middle space is actually empty. That space is what we call as octahedral void. Okay? The middle space, or this space, is what we call as octahedral void. Students, is it clear? Any doubt in this? Are you able to follow? Right? So, in crystal,
Yes, sir.
in crystal we have 2 types of voids, tetrahedral void and octahedral void. Okay, this is how tetrahedral void is formed, and this is how octahedral voids are formed. Okay, then one important thing you should keep in mind that suppose if you have a crystal, okay, I have a crystal containing n atoms, crystal containing, or crystal made up of n atoms. If crystal contains n atoms, listen, that crystal consists of tetrahedral voids and octahedral voids. How many tetrahedral voids and how many octahedral voids, okay, will exist for a crystal containing n atoms? If a crystal is formed, listen, whatever may be the crystal, it may be cubic crystal, hexagonal crystal, whatever may be the crystal, right? If a crystal is formed with n atoms, then there will be 2n tetrahedral voids exist. 2n tetrahedral voids and n number of octahedral voids are formed. Remember, this is very, very important. Whatever crystal you take, if a crystal consists of n atoms, right, there must be 2n tetrahedral voids must exist and n octahedral voids must exist. Okay, this is very, very important. Keep it in mind. Okay, now let me just show you with another way of observing this tetrahedral and octahedral voids. Okay, let me take an unit cell like this. I'm just drawing a cubic unit cell just to show you how tetrahedral voids and octahedral voids, right, present in cubic unit cell. Don't worry about this diagram. By practice, you can easily do that, but right now it is not necessary. Students, see, this is actually one unit cell. I have divided the unit cell into 8 small cubes, above 4 and below 4. Students, we have one unit cell, one cubic unit cell. I have divided that unit cell into 8 cubes. Above we have 4 cubes and below we have 4 cubes. Okay, now listen, just for understanding purpose, I will take sodium chloride crystal. Sodium chloride crystal. Okay, I'll represent sodium ions with the red color circle, and I'll represent chloride ion with the blue circles. Okay, chloride ion with the blue circles. Right, so blue indicate chloride ion and red indicate sodium ion. Okay, now listen how the sodium chloride unit cell, right, actually made up of, right? Chloride ions present at the corners. Students, observe this carefully. Chloride ions present at the corners as well as at the face centers. Chloride ions present at the corners as well as the face centers. All the corners and face centers are occupied by chloride ions. Okay, in sodium chloride crystal. What about sodium ion? Sodium ion occupy all the edge centers. Okay, I missed this corner. I'm sorry. This is another chloride ion. Okay, chloride ion occupy all the corners and all the face centers, front face center and back face center. This is actually one unit cell. In this unit cell, chloride ion occupy all the corners and all the face centers. Now I'll show you sodium ions. Sodium ion occupy all the edge centers. Edge centers are occupied by sodium ions. Sodium ion occupy edge centers. These are all called edge centers. So a cube has 12 edges. So all the edge centers, right, are occupied by sodium ions, and one sodium ion is present at the middle. One sodium ion is present at the middle of the unit cell. This is the structure of sodium chloride unit cell. Structure of sodium chloride unit cell. Okay. Now, in this, students, observe this carefully. See the middle sodium ion. See the middle sodium. How many chloride ions present adjacent to the middle sodium ion, or close to the middle sodium ion? Middle one is sodium ion, right? And how many chloride ions, okay, are present close to the sodium ion?
2, sir.
Observe this carefully. This is a chloride ion 1. This is chloride ion 2, 3, 4, top 5, bottom 6, correct? Am I right, students? So,
Yes, sir.
in sodium chloride crystal, listen, sodium ions are present, okay, in the middle of an octahedron formed by chloride ion. Right? See, these 4 atoms of chloride ion, and I have one atom at the top, one atom at the bottom. If you connect the centers of the chloride ions, students, you connect the centers of the chloride ions. If you connect the centers of the chloride ions, you will get an octahedron. And the middle sodium ion is present in the octahedral void. Am I right? Actually, sodium ions, right? Let me write here. In sodium chloride crystal, sodium ions, Na plus ions present in octahedral voids. In octahedral voids. That's very important. Chloride ions forms the FCC. Chloride ions forms FCC unit cell. Correct? Because chloride ions occupy all the corners and all the face centers. So chloride ion forms the FCC unit cell. Sodium ions occupy right octahedral voids. Right? Sodium ion occupy octahedral voids. Okay, that is very, very important. And remember, which are all the positions are octahedral voids? Students, listen here. The middle one is an octahedral void, and all edge centers are also octahedral voids. Keep that in mind. They are also octahedral voids. So, suppose if a cube is given, if they ask which are all the positions are octahedral void, very simple. The cube center is an octahedral void. Cube center is an octahedral void, and all edge centers are also octahedral voids. In general, this is the way you have to imagine. Okay. If a cubic crystal is given, in the cubic crystal, okay, to identify the octahedral void positions of octahedral void, okay, you see the center and edge centers. Center of the unit cell is an octahedral void, and all edge centers are also octahedral voids. Usually in cubic crystal it will exist like this. Alright. What about tetrahedral void? Listen, in this I have divided this unit cell into 8 small cubes. Okay. The centers of each cube, the centers of each small cube is a tetrahedral void. Is a tetrahedral void. Right? Let me show you in the next structure. Listen, students, observe this. Let me draw that same thing again, and I'll show you the tetrahedral void. The positions of tetrahedral voids in cubic crystals. How to locate the positions. So this is one unit cell. Now listen, students, I have divided the unit cell into small cubes, 8 small cubes. Okay. Now you see this bottom small cube, and I'll place an atom at the center. Okay, I'll place an atom at the center of the bottom cube. Okay, so this is the center of the bottom unit cell, and now I'll place 4 atoms here. See, I'll place 4 atoms. One atom here, 1. Then I'll place an atom here, 2. Then atom here, 3, and an atom here, 4. Right? Actually, this atom is not present in the corner. It is actually present in the center. Okay. Let me just show you like this. Okay. Yeah, this is actually present at the center of the small unit cell. Now, see, if you join the centers of these 4 atoms, okay, if you join the centers of these 4 atoms, right, you will get a tetrahedron. You get a tetrahedron, and this middle point is what we call as a tetrahedral void. This is a tetrahedral void. Tetrahedral void, I wrote simply TV. Tetrahedral void. So, just to make you understand what is octahedral void, what is tetrahedral void, and where it is actually present in the cubic crystal. right? Remember, a crystal consists of octahedral voids as well as tetrahedral voids. If a crystal is formed by n atoms,